Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on theory of numbers, lecture number 41, in which I will discuss on reduced residue system modulo n. Before giving the concept of reduced system modulo n, I would like to give you some background such that you may understand the concept very easily. Let we have a number n equal to 14. Positive integers not exceeding 14 and they are relatively prime to 14, be 3, 5, 1, 9, 11, 13. Here GCD of any of these numbers with 14 be 1. Therefore, these integers are relatively prime to 14 and these are not exceeding 14 and also these are positive integers. So 5 14 equal to number of these integers means 6. Let set of these integers is denoted by A. Here we see that no two integers of A are congruent modulo 14. If we take 11 is congruent to 5 modulo 14. Here 11 minus 5 is 6, which is not divisible by 14. So 11 is not congruent to 5 modulo 14. In this way, we may take any of these two. They are not congruent to each other modulo 14. Therefore, number 1, we get any of these numbers. Let Ri belongs to A, I 1, 2, 3, 4, 5, 6 and GCD of Ri with 14 equal to 1. Number 2, Ri is not congruent to Rj modulo 14. Ij equal to 1, 2, 3, 4, 5. In place of 6 we may write 5 14. Euler's 5 function and this equal to 6. Number 1 represents that each Ri is relatively prime to 14 and number 2 represents that no two elements of A are congruent to each other modulo 14. We may think this in other way also. Let B be a set containing elements 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. When any integer is divided by 14, then we get the remainder which belongs to set B. Here we see that set A is subset of set B. Therefore, set A contains all those remainders when any integer is divided by 14 such that these remainders are relatively prime to 14. Therefore, elements of A are those residues modulo 14 such that these residues are relatively prime to 14. Now let small a is an integer such that A is relatively prime to 14, that is GCD of A and 14 equal to 1. Here we may take A equal to 3, and if we multiply each element of set A by this small a, that is by 3, we get integers 9, 15, 3, 27, 33 and 39. Let C be a set containing these integers. We may verify that each integer belong to C be relatively prime to 14, and also we may verify that no two integers of C are congruent to each other modulo 14. Since randomly we may take that 33 is not congruent to 3 modulo 14. Therefore, the set C contains 514 number of integers, and each integer of C is relatively prime to 14, and no two integers of C are congruent to each other modulo 14. Now, with the help of these concepts, we define the reduced residue modulo n. Now, we define reduced residue system modulo n. A reduced residue system modulo n is a set S of phi n be the Euler's phi function of n, phi n integers such that each element of the set is relatively prime to n, and no two different elements of the set are congruent modulo n. Therefore, S is a reduced residue system modulo m. Double implication. Number 1, X belongs to a capital S implies that GCD of X and n equal to 1. Number 2, X is not congruent to Y modulo n for all X, Y belong to S and X not equal to Y. Now, we prove a theorem. Theorem is let R1, R2, ... r phi n be reduced system modulo n. Here phi n be the Euler's phi function of n. If a is a positive integer with GCD of a and n equal to 1, that means a is relatively prime to n. Then AR1, AR2, AR phi n is also a reduced system modulo n. Further, AR1 multiply AR2 multiply AR phi n is congruent to R1 multiply R2 multiply R phi n modulo n. Now we prove this. Let n equal to a positive integer. Phi n equal to Euler's phi function of n. A is a set containing integers r1, r2, r phi n. r1, r2, r phi n be reduced system modulo n. Therefore, number 1, GCD of Ri and n equal to 1. I 1 2 phi n. Number 2, Ri is not congruent to Rj modulo n. I not equal to j and Ij equal to 1 2 phi n. Now let a be a positive integer such that GCD of a and n equal to 1. Now B is a set containing integers AR1, AR2 AR phi n. We have to show that elements of B reduced system modulo n. If possible, let GCD of A, Ri and n not equal to 1 for at least one I equal to 1 2 phi n. Therefore, GCD of ARI and N greater than 1. This is number 4. Therefore, there exists a prime number P such that P divides GCD of ARI and N, implies that P divides ARI and P divides N, implies that P divides A and P divides N, or P divides Ri and P divides N, implies that P divides GCD of A and N, or P divides GCD of Ri and N. This is number 5 and this is number 6. Since in 2 GCD of A and N equal to 1, therefore from 5 P divides 1. This is number 7. Again, from 1 GCD of Ri and N equal to 1. Therefore, from 6 P divides 1. This is number 8. Therefore, from 7 and 8 we get that P divides 1, but P is greater than equal to 2. Therefore, P divides 1 is impossible. Hence, our assumption in 4 is wrong. Therefore, GCD of ARI and N equal to 1. This is 9. Again, if possible, let ARI is congruent to ARJ modulo N. This is number 10. Since GCD of A and N equal to 1, therefore from 10 we get Ri is congruent to Rj modulo N, which is against number 2. Therefore, our assumption in 10 is wrong. That is, ARI is not congruent to ARJ modulo N. I not equal to J and IJ equal to 1, 2, phi N. This is number 11. Therefore, from 9 and 11, we get that elements belong to set B are reduced system modulo N. Proved. Since sets A and B have the same least positive residue modulo N in some order. Therefore, AR1 multiply AR2 multiply AR phi N is congruent to R1 multiply R2 multiply R phi N modulo N. Again proved. Now we give an example. Let A be a set containing integers 1, 2, 3, 4. This is a reduced system modulo 5. Since 5 equal to 4, the positive integers not exceeding 5 are 1, 2, 3, 4. Therefore, number is 1, 2, 3, 4. So, 5 equal to 4. Since GCD of 2 and 5 equal to 1, that is 2 is relatively prime to 5. Let A equal to 2. Now, two multiply by 1 equal to 2. 2 multiply by 2 equal to 4. 2 multiply 3 equal to 6. 2 multiply 4 equal to 8. Let B is a set containing these integers 2, 4, 6, 8. Here we see that GCD of 2 and 5 equal to 1. GCD of 4 and 5 equal to 1. GCD of 6 and 5 equal to 1 and GCD of 8 and 5 equal to 1. Therefore, each integer of B is relatively prime to 5. Also, if we take any two integers of B, let 2 and 4, 4 is not congruent to 2 modulo 5 because 4 minus 2 equal to 2 is not divisible by 5. Similarly, if we take any two elements of B, we get that any two elements of B are not congruent to each other modulo 5. Therefore, elements of B are reduced system modulo 5. Again, since 2 multiply 1 is congruent to 2 modulo 5 because 2 minus 2 equal to 0 is divisible by 5. 2 multiply by 2 equal to 4 is congruent to 4 modulo 5 because 4 2 multiply by 2 4 minus 4 is divisible by 5. Now 2 multiply 3 6. When 6 is divided by 5, we get remainder 1. So remainder 1 modulo 5. 2 multiply 4 is congruent to 2 4s are 8. When 8 is divided by 5, we get remainder 3 modulo 5. So 2 multiply 1 multiply 2 multiply 2 multiply 2 multiply 3 multiply 2 multiply 4 is congruent to 2 multiply 4 multiply 1 multiply 3 modulo 5. Here we get that these 2 when divided by 5 get remainder 2. This 4 is divided by 5, we get remainder 4. 6 is divided by 5, we get remainder 1. And when 8 is divided by 5, we get remainder 3. So these numbers 1, 2, 3, 4 are same as elements of A, but not in same order. So we may write 2 multiply 1 multiply 2 multiply 2 multiply 2 multiply 3 multiply 2 multiply 4 congruent to 1 multiply 2 multiply 3 multiply 4 modulo 5. In previous theorem, we get same type of result. Here A multiply R1 multiply A multiply R2 multiply A multiply R3 multiply A multiply R4, that is R55 is congruent to R1 multiply R2 multiply R3 multiply R5 modulo 5 modulo n. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.